Kate Shanks. I'm the staff scientist at the FAST Beamline at CHEXS. FAST stands for Forming and Shaping Technology, and that refers to the science mission of the Beamline, which is to investigate and understand and solve performance and processing issues in the field of structural materials. FAST focuses on sort of high energy monochromatic techniques in both diffraction and imaging. And in particular, applying those ways of probing specimens to kind of in situ sample environments so that we can investigate the microstructure of materials while they are being mechanically loaded, while they're being thermally cycled, and also in kind of more high-speed, time-resolved ways as materials are actually being processed or even built up in like a 3D printing architecture. We primarily look at, as I said, structural materials, which is a term that refers to kind of largely engineering materials, so things like cements, ceramics, various metal alloys that are used in applications where their purpose is to bear some kind of mechanical load. So that's in contrast to what some people might refer to as like a functional material, which is more, we're interested in those for like their electrical properties or their magnetic properties. Here, we're primarily looking at things that are of interest for their mechanical properties. And the goal is to build an understanding of how the microstructure of the specimen relates to its mechanical properties. So things like its strength, its brittleness versus ductility, and in particular, one big question is how do materials fail? So what happens to the microstructure when the material cracks or gets crushed or gets pulled apart, things like that. An example of an experiment like that we did this past fall that I thought was especially fun was looking at the mechanical properties of basically moon cement. So a cement made of moon rocks. And so the idea behind that is that if we as like a civilization ever want to start building infrastructure on the moon or in space, we are not going to want to carry all of our construction materials up from Earth with us because that would be prohibitively heavy. We would instead want to be able to make things like cement out of raw materials on, say, the moon, if we were going to try to build a research station there or colonize it or what have you. But before we do that, we would want to know, how does moon cement compare to Earth cement in terms of its mechanical properties and loading behavior? So this was with researchers at Penn State, and they had not literal moon rocks, but cement made with a lunar regolith simulant. So that's a synthetic material that is made to mimic the composition and properties of rocks found on the moon. So they made cement out of this simulant material, and we put it in our RAMS load frame and watched its microstructure evolve as it was crushed. Up and coming experiments that I'm really excited about developing are in situ time resolved studies of additive manufacturing processes for metals. So additive manufacturing, kind of AKA 3D printing, is like kind of an exciting developing alternative to traditional machining. And having kind of robust, reliable, and well understood additive manufacturing techniques for metal alloys would open up a lot of new opportunities and kind of ways to build engineering components. So like stuff for airplanes, stuff for machining, stuff for medical devices. It potentially lets you make things maybe cheaper, lets you make unique components on the fly just by loading up, a CAD drawing into your 3D printer and push and go, as opposed to having to have an entire supply chain and machining line already set up to, do traditional machining to make specific components. However, we need to understand the kind of microstructure and composition of metallic alloys that are made via 3D printing, because they're very different than things made via conventional machining techniques. So at FAST, we have high enough energy X-rays and bright enough X-rays, and we are starting to have fast enough detectors to put an additive manufacturing chamber into the beamline and watch in real time as a part is built up through like laser heating of metal powders and things of that nature. And we can see how the microstructure evolves in the kind of millisecond, potentially down into the nanosecond regime. Yeah, so remote access is actually going extremely well. I was thinking about this, and I think for a lot of us in the synchrotron community, the experience of sort of being at the beamline is like such a unique experience, and it's so immersive. And honestly, it's really fun that a lot of us maybe had trouble in imagining like replacing that or replicating it with anything other than a group, coming here and sitting at the beamline. But remote access, I think, has succeeded in doing that. And I see that in the user groups I've been working with, who keep saying, like, oh, I was kind of skeptical about this, but it's like we're at the beamline. And so that feels like a big success. And that's completely to the credit of the kind of class IT staff and operational staff that has made remote access run really smoothly. And it's a really good approximation of being here. Parts that go into airplanes, parts that go into medical devices, building materials, all these kind of things that impact our daily lives in many different ways. We'll be able to do all of that better if we know how to tell when a part is going to fail, and if we know how to make kind of better, more durable, longer lasting parts more cheaply, kind of more effectively. And if we can start building more predictive models for material performance, that will go a long way to making better engineering components for our buildings and planes and infrastructure. So it's kind of like corny to say this as an X-ray scientist, but literally the future at FAST looks brighter. So in the coming year, we're looking at upgrades to the upstream optics that will give us a brighter monochromatic beam, which will enable more time-resolved studies of materials processing and just more in situ, more time resolved, more realistic conditions for how these materials actually behave in their real-world applications. There was a professor I had for physics when I was in college who used to say, you can't be a scientist by yourself. And I think there's a lot of truth in that. And so from that perspective, I really love working as a part of a big team, getting to work with all these different user groups. There's always kind of something new to learn or something new to try. And you get to do those things with experts. And that is just a fantastic place to work.